Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to welcome you all to this joint webinar series organized by Chemistry Department, Faculty of Sciences and Mathematics, Universitas Diponegoro, and Chemical Science Program, School of Distance Education, University Sains Malaysia. Two speakers will give talks into this joint webinar series. First speaker from Chemical Science Program, USM, by Dr. Sumiyyah Sabar, PhD, MMIC, MRSC, PTech. Good afternoon, Dr. Sumiyyah Sabar. And then the second speaker from Chemistry Department Universitas Diponegoro, Profesor Adi Darmawan, SSI, MSI, PhD. Selamat siang, Prof. Adi. So before the presentation begin, allow me to read today's joint webinar outline. So first opening speech from Head of Chemical Science Program, Dr. Tanwini. And then the second talk by first speaker from USM, and the third one is talked by second speaker from Universitas Diponegoro, Undip, and then after that Q&A, and the last is closing. So before going further, please welcome Dr. Tanwini to give opening speech. Please welcome Dr. Tan.
Okay, thank you, Dr. Yayu. Okay, so first of all, I would like to take this opportunity to thank the Chemistry Department, Faculty of Science and Mathematics, Universitas Diponegoro, Undip, for making this joint webinar success. So this is our second joint webinar so far, and we have 4 more sessions planned until November 2024. So I believe that this joint webinar will serve as an initiation for both Undip and USM to collaborate and also learn more about each other's research fields to make better research matching for our future collaborations in terms of publications, student supervision, grant applications, and many more. So at the Chemical Sciences Program, School of Distance Education, USM, we always welcome any form of collaboration with Undip. So be it through any mobility programs or any student exchange initiative. So lastly, I would like to express my gratitude once again to the committee for this joint webinar, especially to Dr. Yayut, who has been a key person for this success. Thank you.
Okay, thank you very much, Dr. Tan, for short opening speech for this joint webinar. So then we move to the second part, talk by the first speaker will be delivered by Dr. Sumiyyah Sabar. She is going to talk about synergistic adsorption-photocatalytic processes for enhanced wastewater treatment. Before the presentation begin, allow me to introduce Dr. Sumiyyah Sabar. Let me share her CV. So, Dr. Sumiyyah Sabar, PhD, MMIC, MRSC, PTech, Senior Lecturer at Chemical Sciences Program, School of Distance Education, Universiti Sains Malaysia, Malaysia. And this is her email, sumiyyah@usm.my. And then her research interests are photocatalytic materials, functional adsorbent, hybrid nanomaterials, biopolymers, and water and wastewater treatment. For the publication, Dr. Sumiyyah Sabar has the total number of citation in Google Scholar around 2,500 more, and in Scopus around 2,100 more. And the H index in Google Scholar is around 23, and in Scopus 22. For the total publication in Google Scholar 49, and then in Scopus around 43. And her educational background, she obtained a PhD award in photocatalyst in 2013 in University Sains Malaysia, and then she received a BSc Analytical and Environmental Chemistry 2007 in University Malaysia Terengganu. And then professional experience, senior lecturer at School of Distance Education USM, visiting researcher in Osaka University, credit auditor, visiting researcher, postdoctoral researcher, professional technologies, editors in Malaysian Journal of Analytical Sciences, and then member of Royal Society of Chemistry and associate member Malaysian Institute of Chemistry. And then some award also she received, Good Medal Awards, Chemistry Invention and Innovation, Ministry of Science, Technology and Innovation Malaysia, Good Medal and Best Award, International Conference and Exposition on Invention by Institution of Higher Learning, Ministry of Higher Education Malaysia, Travel Grant Award, Guest Lecturer in Global Learning Program, in ITS. Also, Dr. Sumiyyah was already coming to Indonesia. Yeah, Travel Grant Award in higher education in disruptive landscape. And then scholarship, Matsumai International Foundation Research Fellowship Japan 2024. So that's why she is now in Osaka, I guess. And then the second one, postdoctoral scholarship, Ministry of Higher Education Malaysia in 2018. Wow, it's wonderful CV, Dr. Sumiyyah. Dr. Sumiyyah, you have around 25 to 30 minutes to give a talk. And then after that will be continued by the second speaker. The last is Q&A. Okay, so Dr. Sumiyyah, please, time is yours now.
Thank you, Dr. Yayu. Assalamualaikum and a very good day. I'm sharing my screen now. Can you see my screen?
Yes, yes.
Okay. Thank you for this invitation to share a little bit about my research area on photocatalysis. I'm so grateful to UNDIP for this opportunity. So this topic, today's topic that I would like to share with you is from my PhD project, and then some research work from my collaboration with my students and other colleagues. So the topic is synergistic adsorption photocatalytic process for enhanced wastewater treatment. So just how much fresh water is there on Earth? So if you look at this is the common picture of the Earth. Okay, you can see that it's almost blue, giving the illustration that our Earth is covered by water. Okay, we assume that we have abundance of water. If you compare, this is the volume of the Earth, and then here we have droplets, water droplets. You can compare the volume of this water droplet as compared to the size of the Earth. Actually, even though about 71% of the Earth is covered with water, but it's only a thin layer as compared to the volume of the Earth. And this water droplet indicates that 2.5% of the water is suitable for human consumption. However, if you can see these small tiny dots here, this is only what is actually accessible to us, because most of this water, 2.5%, is stored in a glacier or ice, so it's not accessible to us. So the about less than 1% of fresh water is accessible to us. So where can we get this 1% of fresh water? It can come from rivers, groundwater, lake, dam, or ponds. Okay, so it's a fresh water. While most of the water that is available is salt water. So is there any clean and safe water for us or our future generation. So it has been estimated that about 1,000 of children and kids die every day because of the lack of clean water and sanitation-related diseases around the world. So water pollution is a global issue. And in Malaysia, we also have problem with wastewater or water problem in some news article related to the chemical waste pollution in Sungai Kim Kim in Johor. This is where USMR, we also have a water problem in Penang, and also there are water issues in our capital city, Kuala Lumpur, where the Klang Valley River water supply is always at risk because of water pollution. So because of the serious of this issue is the United Nations under the Sustainable Development Goals have targeted one goal specific to water, which is clean water and sanitation, SDG 6. So under SDG 6, there are a few targets, and one of the target 6.3, is to improve water and water quality, wastewater treatment, and safe reuse. So there are a few wastewater treatment methods available. The first one is biological treatment. For example, you have the aerobic digestion, anaerobic digestion, or biodegradation. The second one is physical or chemical treatment, such as adsorption, coagulation, flocculation, or filtration. So these are common methods used in a commercial wastewater treatment plant. And advanced oxidation process, which is currently on emerging. Not many wastewater treatment plant has implemented this method yet because it's under intense study, such as chemical oxidation, ozonation, electrochemical photolysis, and photocatalysis. So today my topic will be focused on photocatalysis. So what is a photocatalysis? So photocatalysis is termed as a photo-induced reaction, which is accelerated by the presence of a catalyst. So if you know about catalyst is, it does not change itself during a chemical reaction or being consumed during a chemical reaction. So if you can compare this analogy of photocatalysis with photosynthesis, for photosynthesis, you have chlorophyll, where it absorbs photon energy from the sun in the presence of water and carbon dioxide to produce energy in the form of starch and oxygen. So a similar concept to photosynthesis. For photocatalysis, you need a photocatalyst that are able to absorb photon energy from any light source, and it can convert organic compound in the presence of water and oxygen to produce carbon dioxide and water. So the photoreaction is characterized by the free radical mechanism initiated by the absorption of a photon with sufficient energy. So this energy that is provided by the light source must be equal or higher than the band gap energy of the photocatalyst. So this is the basic mechanism of the photocatalyst. So for a photoreaction to occur, there are three important components that is needed. One, we have to have a photon energy. So this photon energy must have an appropriate wavelength, and the energy must be equal or higher than the band gap energy of the photocatalyst. So the second component is that you need a photocatalyst, of course. And this photocatalyst is normally a semiconductor where it has the valence band where you have the highest occupied energy band, and you have the conduction band where is the lowest occupied band, and in the middle you have a gap, what we know as a band gap. So here the third component that you need is a strong oxidizing agent. So in this case, normally we provided like oxygen, where when this photocatalyst absorb the photon energy, there will be a charge separation between the electron and positive hole. So when the charge are excited, the electron are excited from the valence band to the conduction band, this electron will undergo reduction reaction in the presence of electron acceptor. While on the other hand, the positive hole at the valence band will undergo oxidation in the presence of electron donor. So this is the basic mechanism of the photo-induced excitation generation. As see here is the semiconductor. With the photon energy, it will produce the charge separation between the positive hole and electron. And then at the valence band here, it would undergo oxidation reaction, which in the end will produce hydroxy radical. And then at the conduction band, it will undergo reduction reaction to produce also the hydroxy radical. So in this case, there are few oxidative radicals being formed, such as hydroxy radicals, superoxide radicals that are highly oxidizing and can mineralize organic pollutants into CO2 and water. So what is the advantages of a photocatalysis? It can produce a complete mineralization. By right, if you have sufficient energy, you have a good charge separation, all the organic pollutant can be oxidized into CO2 and water. So in this case, you have a complete mineralization. Second, it does not produce secondary pollutant. Some wastewater treatment method, it can produce a secondary pollutant such as sludge formation, which then need to be treated off. There's no waste disposal problem. For example, like coagulation method, you have to deal with the sludge formation, how to dispose them, because you cannot just simply throw it away anywhere. It must be fully treated, the sludge. Is inexpensive and economic saving. You need only light source. This light source, we can use sunlight, which is abundant. And the photo reaction can be conducted under mild condition. It does not have to be conducted under extreme temperature or pressure. So one of the common photocatalysts being used in wastewater treatment is titanium dioxide. So titanium dioxide is a transition metal oxide, which is a natural occurring form of titanium. It's also known as titania or titanium oxide. It has a lot of advantages as compared to other semiconductor. For example, it's chemically and biologically inert, photocatalytically and thermally stable. It has a high photoconductivity, and because of that, it's not only used for wastewater treatment, it's also used for water splitting or hydrogen production, hydrogen peroxide production, and so on. The photo-generated holes are highly oxidizing. It's relatively easy to produce and to use. It has long durability and cheap, and also safe to human. Also safe to human and the environment. So titanium dioxide has also been widely used as a coating material in paint and so on. So it's been established that it is safe and non-toxic. So there are 3 types of crystal structure of titanium dioxide known so far, which are rutile, bruchite, and anatase. So the most widely used type of titanium dioxide is the anatase phase, because anatase is stable. It has a high photo conductivity and so on. While the least used type of titanium dioxide is the bruchite type because of its complex structure and also unstable. However, there are a few drawbacks of using titanium dioxide alone. Okay, it has low reaction rate and poor adsorption ability. So when you have a poor adsorption ability, it's difficult to attract the pollutant to the surface of the photocatalyst. It has large band gap energy and low quantum efficiency. So it has a band gap energy of 3.2 electron volt. So this makes it only active under ultraviolet radiation. So if we want to fully utilize it for solar photocatalysis, then it's not very good because there are only about 5% of UV in the our solar. So we need to shift the activity of the titanium dioxide towards the visible light region. And it has a high recombination rate of photo-induced electron hole pairs. So in this case, if the excited electron tend to recombine back with the positive holes, so then it will slow down the reaction because the electron cannot participate in the reduction reaction or oxidation reaction. And it's difficult to regenerate, recover, and reuse of titanium dioxide because titanium dioxide is a very fine powder, and when you use it for wastewater treatment especially, it's difficult to recover back this powder after it's being used. So one way to solve this problem is by combining titanium dioxide with adsorbent materials. So there are many types of adsorbent material that can be utilized to improve the photocatalytic activity. For example, activated carbon-based adsorbent. So activated carbon can be obtained from any natural sources, or while it can also be obtained from commercial activated carbon. But the low-cost approach is from the waste materials such as rice husks, orange peel, sodas, and so on. We can also combine titanium dioxide with other metal oxide that have high adsorption properties. For example, iron oxide or iron oxide nanoparticle, zinc oxide, and so on. And recently, there's also an increased study on metal organic frameworks, or MOF. So MOF have a large surface area, so it has the tendency to attract water pollutant. And non-conventional adsorbents such as neem leaf powder, maize cob, coal fly ash, eggshell waste, or chitosan. And then we also have hybrid nanoadsorbent such as carbon nanotube, graphene and its composite, and a layer double hydroxide. Or polymer-based nanoadsorbent such as polyaniline or polypropyl. So I will discuss a bit what our group have been working on so far. So the first work was started when we tried to combine titanium dioxide with chitosan. So why chitosan? Because chitosan is a low cost and abundant natural source that we can obtain from the acetylation of chitin. So this chitin can be obtained from shell of crustacean such as prawn or crab. So it's abundant, it's low cost, it's non-toxic, it's biodegradable, it has a very good film forming ability, and so on. So what we did was that we tried to immobilize the chitosan onto a glass plate, and then we prepare a Ti2 formulation, which is made from ENR50, which is epoxy natural rubber, acetonitrile, and also phenol formaldehyde. So all the Ti2 formulation was prepared, and then it was we deep coat this Ti2 formulation onto the immobilized chitosan, and you will get this immobilized Ti2 chitosan. So if you can see from the cross section of this material, we have the glass plate as the support, and then we have the chitosan as the second layer, and Ti2 is at the top. So this is what we call a layer by layer titanium dioxide chitosan glass. So when in this case, we have done a pre-treatment on this immobilized titanium chitosan, where we observe that if we irradiate this layer in water, in the presence of a photon energy from we use only a fluorescent light as a low cost and easily accessible light source, we observe that the ENR, the epoxy nitrile rubber, started to degrade during the irradiation. So in this case, the ENR act as a pore forming agent where it start to form micropores on the chitosan. On the TiO2 surface. Okay, so you can see the difference in the SEM images of the layer. This is the top layer, the titanium layer, where this is for without any irradiation, the initial surface of the titanium dioxide. This is after 6 hours, and this is after 10 hours of irradiation. You can clearly see that there are micropores forming on the titanium dioxide. So when these pores are formed, it allows better diffusion of the pollutant and also the light penetration to the chitosan. Okay, and then we did a control experiment where we compare the activity of the photocatalyst with adsorption and also photolysis using phenol as the pollutant. And we see that there is no photolysis. Photolysis means that only in the presence of the pollutant and the light irradiation, without the presence of the photocatalyst, we observe there is no degradation occur. And the adsorption is only very little. So this means that phenol is not really absorbing onto the chitosan or titanium dioxide. So then we compare. This is titanium only, okay, without the presence of chitosan. This here is the titanium dioxide and chitosan. And we observe that the activity or the photocatalytic activity of the titanium dioxide chitosan is almost comparable with the Ti2 in powder form. Okay, so we have done characterization, and we have found that actually during the irradiation, the chitosan also undergoes some transformation. Okay, there are some carbonyl group being formed on the chitosan surface, which increase its visible light activity. Okay, so that's why we observe that the titanium dioxide chitosan bilayer is the activity is almost comparable with the slurry TiO2. And we have also repeated the usage of the same samples for 10 cycles of application, and we can see that there's a consistent consistent degradation of phenol by the titanium titanium chitosan bilayer, and this is way better than the Ti2 single layer. And on Ti2 slurry, it can only be used for one time only because it's difficult to recover the powder. And the photocatalysts also have shown a good mineralization performance, which is measured via COD analysis. Okay, and we observed that the Ti2 chitosan bilayer has a very good mineralization rate. So this work has been published in 2 articles. And sorry, my slide is not moving. Okay. Wait, let me go back. Okay, so next one. So in the previous study, the phenol, the pollutant, does not have any adsorption activity towards the photocatalyst or the chitosan. Okay, so now we try to test. We change the pollutant into by using dye, which is reactive REACT4 or RR4. So we have obtained that now there's an increase in the adsorption properties of the pollutant. So this is the first line here is the Ti2 only adsorption. There's no activity, no adsorption properties by the titanium dioxide for reactive RAD4. And then this is the Ti2 under irradiation, which is in the presence of light. So you can see little improvement in the titanium dioxide only. And then when we combine titanium dioxide with chitosan, you can see an insignificant increase in the adsorption performance of the photocatalyst. And the removal under photocatalysis is even better. So if you can compare the rates of the photodegradation, you can see that the rate of titanium dioxide, chitosan, is about 32 times higher as compared to Ti2 alone. Okay. And this is the proposed mechanism that was involved during the photocatalytic decolorization of reactive RAD4 dye. There are three main steps which involve in this degradation. The first one is the direct adsorption of the dye onto the chitosan layer. So these dye, they are not being degraded, they directly adsorb onto the chitosan layer. And then the second one is the direct photocatalytic degradation of the dye by the titanium dioxide. So it's only on the surface of the photocatalyst where the dye is being degraded. And the third one, we observe that the adsorbed dye in the chitosan layer also participate in the reaction by involving the charge transfer from the oxidation of the adsorbed dye into the titanium chitosan interface, where the charge is being transferred into the conduction band of Ti2. So it further enhances the degradation of the dye. So after that, we want to confirm whether, you know, the adsorbed dye really contribute to the charge transfer, really contribute to the enhanced photocatalytic activity of the pollutant. So in this case, we try to mimic, we use reactive red dye as a photosensitizer. Okay, so we have the similar setup. Now we fully adsorb this chitosan with reactive RAD4 dye, and then we coat it with titanium dioxide. So this is titanium R4 chitosan glass. And we observe that there's a shift in the visible light region due to the presence of the dye. And in fact, for the photoluminescence analysis, we also observe a decrease in the intensity of the PL peak. So this indicates that the recombination rate of the electron is better in the presence of the dye. So we did, to avoid any other adsorption occurring on the surface of the photocatalyst, so we use phenol as the model pollutant. So in this case, we observed that the adsorption is poor on the photocatalyst because phenol does not have a good adsorption on chitosan. And we observe that in the presence of the dye, the degradation was much better as compared to Ti2 chitosan only. So this enhances our prediction, support our prediction that there are actually a charge transfer occur between in the presence of the dye in the chitosan layer. Okay, so for the phenol degradation, there are only two mechanisms involved: direct photocatalysis and also the charge transfer from the oxidation of the chemisol for dye onto the Tl2. So there is no adsorption occur, but because of these two mechanisms that occur concurrently, so it improves the degradation of phenol. Next, we try to change the chitosan. We try to modify the chitosan because chitosan is not a porous material, it's a polymer. So it has a very compact, dense structure. And so we try to make it more porous. by combining it with monomolar. Okay, so we observed that when we add or which modify the chitosan, it has improved the visible light active of the photocatalyst. And it can be seen that once we add the monomolar into the chitosan, the band gap energy has decreased from 3.03 to 2.93 electron volt. So we also observe that there is an increase in the adsorption properties of the photocatalyst that in the end improve the overall photocatalytic activity. So, and furthermore, the photocatalyst also is reusable. It can be reused up to 10 cycles without any significant decrease in the photocatalytic activity of metal orange. So this study was conducted using a metal orange dye. And these are the mechanism for the degradation of the metal orange. Okay, so the first one is the photolysis of the metal orange, because metal orange is sensitive to a photon, and so it also undergo photolysis. The second one is the direct photocatalytic oxidation by the Ti2 top layer. So this is the cross section of this layer by layer under scanning electron microscope. So you can see that this is the Ti2. And then this is the chitosan monomolar, and then this is the glass plate. Okay, so the adsorbent is only a very thin layer inside the titanium dioxide. Okay, and then the third mechanism is the adsorption by the chitosan empty sublayer, and then the photocatalytic oxidation of adsorbed metal orange by the Ti2 top layer. So again, this is the charge transfer mechanism by the adsorbed dye in the adsorbent layer. Okay, the latest one that we recently did is we try to work with metal organic framework. So there are a few MOF that is being studied by my group right now. So one of them is MIL125, aminated MIL125. Okay, so in this case, our aim is to use MOF to produce adsorbent, to produce photocatalysts that have a good adsorption ability. Okay, so in this case, what we did is that we produced thermolysis of this MOF, okay, under inert condition, where it produces nitrogen doped carbon porous titanium dioxide. Okay, so aminated MIL125 is a Ti-based MOF. So under calcination, it will produce a titanium dioxide. So again here, interestingly, because a MOF is a combination between metal cluster and also organic ligand. So it was found from our study that this organic ligand has converted into a carbon whereby under calcination. Okay, and because there's a presence of amino group, so this amino group contributed to the doping of the nitrogen into the titanium dioxide. So what happened to the mechanism now is that there's a enhanced photocatalytic activity because of the nitrogen doping, where it has decreases the band gap energy of titanium dioxide from 3.2 to 2.86 electron volts. So it has shifted the activity of the photocatalyst into the visible light region, and this carbon it increased the absorption of the photocatalyst, and also it acts as a charge carrier for the electron, the negative electron, and further enhance the reduction of methylene blue dye. So this is the SRD spectra of the aminated MIL125 from the first. This is without any calcination. And then as we increase the temperature of the calcination from 300 to 900, we observe the transformation of the MOF from Mi-125 into titanium dioxide. So this is the top here is the XRD spectra of the commercial titanium dioxide, and we can observe that at 900 degrees Celsius, the titanium dioxide being produced is almost similar to the commercial titanium dioxide. In fact, we have obtained two crystal structure inside this titanium dioxide that we calcine, which is anatase and voltile. So this is the band gap energy of the material of the morph before and after calcination. So you can see that the band gap energy of the morph actually increases, okay, because it's being transformed into titanium dioxide, but the titanium dioxide has a much larger band gap energy as compared to those that we obtain from the thermolysis of the morph. And this is the effect of the catalyst dosage in terms of for the photocatalytic degradation of methylene blue. We observe that the adsorption increases with the increase of the photocatalyst. But you should also be careful so that the adsorption is not dominant towards the photocatalytic reaction. If not, all the dye will be absorbed onto the adsorbent and it will not be degraded. We want the pollutant to be degraded and not just absorbed onto the adsorbent material. So as a conclusion, synergistic adsorption photocatalytic process represent a highly promising approach for enhancing wastewater treatment efficiency. By combining adsorption and photocatalysis, contaminants can be effectively captured and degraded through light activation. And this results in comprehensive pollutant removal, faster degradation rates, and higher treatment efficiency with potential to target a broader range of photocatalysts. So it does not have to be limited into organic pollutant only. It can be also applied to metal or pharmaceutical pollutant. And however, there are several factors that still need to be studied, such as the photocatalyst selection, catalyst modification, adsorbent types, pollutant types, and photoreactor design that need to be further investigated. So last but not least, I would like to thank you to my collaborator, my previous supervisor, Professor Dr. Muhammad Asri, my collaborator, Dr. Nur Naziha, Dr. Ali from UiTM, Dr. Nur Sazwani, she was my previous PhD student, the Associate Professor Dr. Fu Keng Yoon, Shilatina from Syiah Kuala University, Professor Dr. Rafael Schneider from University of Lorraine, and Dr. Veda Abdul Hamid from National Research Center, Egypt. And last but not least, to my lab team, Reticular and Environment Laboratory, for their hard work and their support. Thank you.
Yeah. Thank you very much, Dr. Sumiyyah Sabar. Actually, my research topic is also photocatalyst, so yeah, it's very
Oh,
interesting talk. Yeah, and then
thank you.
you did a lot of project, I guess, and then you make like a film, the IO2 titanium dioxide film, and then you mix with the ketosene and also RR4, and so on, and
Yes.
also morilonate and so on. So it's quite complex. Okay, maybe we can talk a lot later on. But I hope next week we can meet. But you are now in Osaka,
Yes,
unfortunately. Yeah.
I'll be
Okay.
here until March next year.
Oh, March. Okay, okay. Okay, maybe later on. Okay, thank you,
Thank
Dr.
you.
Sumiyyah. Okay, the next speaker, maybe before we go to the next speaker, maybe we can take photo together. Pak Badrul, are you here? Hello, Pak Badrul, can we take a photo together, Pak Badrul? Halo, Pak Badrul.
Okay.
Okay,
Oh,
yeah.
yes.
Okay,
Okay.
Maybe please open your camera, all of the participants, so we can take a photo together. Ya, Pak Badrul, please hitung.
Okay, 1, 2, 3.
Okay,
Wait.
ya, next slide. Until 7, Pak Badrul, I
Next
guess.
slide.
Ya.
Yes. 1, 2, 3. Okay. Right.
Okay, finish.
Yes, yes.
Okay, yeah, thank you, Pak Badrul. Okay, ladies and gentlemen, so now we can move to the second session, talk by the second speaker, which will be delivered by Professor Adi Darmawan with the title Graphene Oxide and Silica Based Membrane for Desalination. And then let me introduce him, even though you all knows very well on him. Yeah, but I think Dr. Tan and her team or her colleagues not yet. So, okay. Yeah, Professor Adi Darmawan, he is a professor at the Department of Chemistry, Faculty of Science and Mathematics, Universitas Diponegoro, Indonesia. And then his research interest is in material, especially in inorganic membrane. And his publication, the total number of citation is about 1,000 more in Google Scholar, and then Scopus around 600. And then his H index in Google Scholar is 17 and in Scopus is 16. And then the total publication in Google Scholar around 100, and then in Scopus around 70. And then his educational background in 2010 to 2014, he received his PhD in School of Chemistry Engineering, the University of Queensland, Brisbane, Australia. And then in 2003, he received MSc degree in Department of Chemistry, Gajah Mada University, Indonesia. And in 1996, he received a BSc in Department of Chemistry, Diponegoro University, Indonesia. And then there are several publications has already published by him with his team actually. So maybe not going. Okay. So next, Professor Adi Darmawan, you have around 25 to 30 minutes to give a talk. So your time is yours, Prof. Adi.
Okay, thank you very much, Muyayu. I would like to share my screen. So, can you see my screen?
Yeah.
Okay. Okay. Today I would like to discuss about graphene oxide and silica-based membrane for desalination. Actually, this is my focus on research, which I start from PhD. When I was a PhD, I studied about the membrane, but for gas separation. But because of the limitation of the equipment, so I moved to the desalination because it's easier. For the gas separation, actually, we need connected GC. So and we don't have here. So I moved to the desalination. Okay. I think it's more. So actually, this is the this topic is already published in the three publication and all the research was conducted by the students. So the first is about from FIGO. This is 2018 student, and the second one from the Finsky is from 2016 student, and the last one from Harizat Zakiyah. Yeah. So I will discuss about this, and okay. As mentioned from Dr. Sumiyyah, that the urgency about the water, and we all that I mentioned before about we have the abundance water in the sea, but we can't use the seawater directly because it's consists of salt. So how to get the seawater, how to make the seawater to be able to be drink is just using the desalination, and most of the desalination technology using the thermal desalination. So it is a very high consume the energy. So there is another technology that using membrane. So actually the membrane is sieving that can separate between the small and the larger species. And this one, in this case, we have to separate between the water and salt. So, and we know that the salt consists of the sodium and chloride ion. So we have to make like here. I show you here. This is the membrane, and we can the water can pass the membrane, and the sodium or the chloride ion can not pass the membrane. So actually, we have to find the very small pore, which is like more is larger than the water kinetic diameter, but smaller than the sodium and chloride, sodium and chloride diameter. Okay, so actually there are two focus of my research is I'm using graphene oxide at the moment, and previously I was using silica. The idea is like silica, the graphene oxide is 2D material, which consists of the multi-layer sheet. You know that we know that we have graphite, but the graphite is not there is no functional group. So we have to change the graphite structure to have more functional groups. So we have to put carboxyl on OH, right? So we have to oxidize this graphic structure to be have more functional group. Yeah, this is the idea. So like this one, you can see this is like brick structure, and there is a pore here, and the pore can pass the water and neglect the sodium and chloride ion. Another material is silica. Also, the material silica is porous material. The pore is very tiny, and also they have the functional group like selenol that can separate ion from based on the charge, and also the silica has the pore that can separate the ion from the based on the size. Yeah. Okay. Okay. This is the publication that already published. The title is a new design of graphene oxide on macroporous nylon assisted polyphenol alcohol from zinc with zinc crosslinker for vaporization desalination. Actually, this this publication was conducted by my student, Angel Navigo. Okay, the idea is we have graphite and we have to oxidize the graphite using the hard acid, strong acid, I mean, strong acid, sulfate, and permanganate, yeah, permanganate. And after that, we got the graphene oxide, yeah, we got the absolute graphene oxide. And the graphene oxide, next, we mix with the VVF, polyphenol alcohol, and cast the GO solution, not solution, mixer between GO and VVA to have and put with this cross linker. So it's like this one. This is like nylon sheet, and in the top of the nylon sheet there is solid, the mixture between the GO and the VVA. After that, we test the membrane using the desalination setup like this one. We are using the perforation system, in which that this is the salt water, and we suck the vapor with it, and the vapor then to be freezing or freeze using in the cold trap, and this is the vacuum chambers, right? Okay. This is the GO sheet, and we know that you can see this is the graphite, the FTIR or the graphite, and you can see that the graphites already changed to the GO, more functional group here, and also the XRD shows that there is a shift from the right to the left, yeah. So it means that the how to say, the space between sorry, as in here I have to. Okay. Sorry. Continue. Yeah. Let me continue. So there is a shift from the right to the left. It means that the size of the GO is larger than the graphite. Yeah. Okay. The next one is we already synthesized the GO. We mix the GO as a membrane. Yeah, so we mix with the VVA, polyphenol alcohol, and the structure of the polyphenol alcohol we call the brick mortar structure. This is like brick, and it's like it's like mortar of the in the building, right? What is the function of the VVA? Is we put the VVA to how to say, to inhibit the swelling of GO, because the GO actually it's easy to be swelled if we infiltrate the water in the middle. Yeah, so the VVA inhibit the swelling of the GO. Okay. And after that, we put like this is the how to say, this is the stability test, and we can see that this is the GO, only the GO, and we can see that only by 1 minute the sonication there is a slight peel off of the surface of the GO, but when we combine with GO, PVA, and the zinc as the cross-linker, it can resist to up to 30 minutes. Yeah, up to 30 minutes. Okay. Maybe I said after that we test the GO PVA membrane with water with the concentration of sodium chloride 1%, 3.5%, and 7%. Actually, for the seawater, the concentration of salt is around 3.5%, but we try to also for the brine water, which is around 7% for the concentration of salt, and up to how to say, the salt rejection. It's mean that the membrane can resist or can inhibit the salt. It's close to 100%. Yeah, for 100%. and the flux is quite good because the water formation is around 20. If we read about the Journal of Membrane Science or Desalination also, or whatever about the desalination, the value of around 20 is quite good, yeah, for the flux. Yeah. Okay, this is the performance of membrane. Also, we test about the temperature, yeah, the temperature at the room temperature is 30, 45, and 60. We know that we can see that here by increasing the temperature, the water flux increase. I think it's easy to be understand because it easy to be understood because actually by increasing the temperature, we increase the driving force, yeah, the driving force of the feed water to pass the membrane. But we can see that even for the room temperature at 30 degrees, the water flux is around 10. That it's mean that we can produce the pure water even from in the room temperature. So actually this membrane can reduce the energy because like if we desalinate water, the salt water from we need to boil the water until 100 degrees. Too much energy because actually the specific heat capacity of water actually very high. So we can reduce the energy, the consumption of energy by using the membrane. Okay. Okay, this is the first publication about this one. Okay. The second one is about using the silica, yeah, because the first one is about using the GO, and the second one is silica layer. Actually, silica is my previous material that I was using silica when I got PhD, but at the time silica shows the very good performance for the gas separation. When I come back to Indonesia, there is no equipment about to research about gas separation, so I moved to the desalination. The problem of silica layer is silica actually has the OH group, which can easily interact with water. So the interaction between the OH group with and water actually can destroy the silica structure. So it's make the silica decrease the performance, reduce the performance. So we have to have an idea how to make the silica structure become more like become because like can resist the water interaction. So the idea is like if we have like lotus, or how to say in bahasa Indonesia daun teratai, I don't know what is the English in English, daun teratai or lotus, right? Lotus leaf or daun keladi. When we put the water in the surface of daun teratai in the lotus leaf, the water is not interact with the surface. The lotus, like the surface become hydrophobic, and the water can't can interact with the material. Yeah, this is the idea. So the idea I try to make the silica is more hydrophobic. Yeah, my hydrophobic using the what we call the hydrophobic agent. Yeah, hydrophobic agent, and in this case I was using the MTMS, methyl 3 methoxysilan, yeah, methyl with methyl 3-methoxysilan. The structure, because actually for the silica research, usually most of the people are using the TEOS and tetraethyl orthosilicate as the main materials. But the problem of the TEOS is TEOS produce the silica with the OH structure, where there is a SiOH structure, which the OH structure can easily interact with water. And so we have to we have to combine the TEOS and TEOS with the MTAS. The MTAS, because of the methyl structure in methyl group in the structure, so the methyl group can make the structures more organic or more hydrophobic. Yeah. Okay, this is the MTAS and TEOS, and you can see here this is table between the composition between the MTAS and TEOS. So first we have the majority is TEOS and 90 and only 10% of the MTAS, and the second one so this is the increase of the MTAS content, and this is the decrease of the TEOS content. Okay. The idea is same. Put the silica, but not like the GO. I'm using nylon support, but for the silica, I'm using the alumina support, because actually this is silica is very brittle. So not we can't use the flexible support like nylon. So I'm using this. I'm using alumina support here. Just so the silica was doped on the surface of the alumina support. The desalination setup is quite same. So you can see that this is the feed, which is the salt water, and I'm using the perforation system, in which that the salt water sucked by the vacuum chambers here, and the vapor of the water was freezed by the cork trap. Actually, this is only the ice, and like how to say in bahasa, but in English is in bahasa Indonesia it's called thermos. Thermos. I just put ice here, and the vapor of the water condensate in the thermos. Yeah. Okay, the idea is the same. The process for the GO and the silica is the same. Okay, this is the characterization. I think I move just move forward to the. I don't discuss about the characterization. Here, this maybe here, that the increasing of the MTAS content in the silica structure, in the silica matrix, actually increase the hydrophobicity of the silica. You can see this is first with 10% of the MTMS. The water content angle is 93. But by increasing the content of the MTAS, the water content angle is around 100 something, yeah, 111, yeah. So by increasing the TEOS composition, the water content angle decrease. By increasing the MTAS content, the water content angles increase, yeah. So actually, by increasing the MTAS, we can say that the hydrophobicity of silica increase. Okay. After that, I try to test the membrane using the in the desalination. And you can see here that by increasing the MTIS, the salt rejection is increased sharply, close to 100 for the MTIS, yeah. And the water flux is decreased slightly, yeah, the water flux is decreased slightly. And we are trying to test this for the long term application until up to 40 hours, and up to 40 hours, the salt rejection still in around 100%. So we can see the membrane is working very well, and the water flux is quite same between 4 until the 6 kilogram per meter per hour. But if we compare the silica with GO, actually the water flux is very low, because what I already said before, that for the GO, the water flux is around 20, but you can see here is only between 4 until 6 kilogram per meter square per hour. Yeah. So one fourth. Yeah. We can say that the GO membrane is better compared to the GO membrane is better compared to the silica membrane. Okay. This is the second publication. The next one, the idea is if we mix the graphene oxide and silicon dioxide, the silica, yeah. So we can this is not the newest, because actually after this one we have another publication, but the second newest publication is the graphene oxide and silicon oxide hybrid coating on zirconia ceramic for sustainable water combination. So this is actually the mix between the GO and silica. Okay. So first we have the same method, produce the GO, and after that GO and TiOS, yeah, GO and TiOS mix together, and we put on the surface of the zirconia tube. Yeah, the zirconia I got from my colleague in the UNLAM, Universitas Lambung Mangkurat. She sent me the tube, and we put here, in the surface. Yeah, the idea is quite the method is quite same. So we were using the perforation method, yeah, the same as before. Okay, this is the characterization. I think we just skip the characterization because it's quite same with GO before. And okay. This is the water quota angle. Also the GO, you can say the Porsche distribution curve shows the similar peak of the, okay, it's quite same, because because we just compare between the GO and the silica. And what's the idea? This is the idea, yeah. How the GO can combine with silica. We propose that the structure is like this one. This is the silica structure, and this is the GO structure, because the silica has OH group, functional group, and also the OGO also have the OH group. So this is the how to say, the hydrogen bond, yeah, hydrogen bond between the OH and H of the OH and H, yeah. Okay. After that, this is not the characteristic. Yeah, this is the performance of membrane. It's quite same. close to 100% for the salt rejection, but the water flux is close to silica. Yeah, close to silica. It's around 4 until 8. Much lower if compared to the GO-VVA membrane. Okay, this is also we do the cycle because the problem of this membrane, that's like what to say, the salting out, like deposit of salt. So we have to we have to clean the membrane, and after that we have to clean and put it in the module again and so on. So we put the membrane until the 18 hours, 18 cycle. Yeah, actually this is 20, but after the 20 the salt reduction decrease, so much decrease, but and the, how to say this here, and the flux increase subtly. Yeah, so we can say that we can use this membrane until 18 cycles, much lower if compared to this GO, right? And for the silica alone. So this is the conclusion. So first we develop the three membrane here. First the GO and VVA. The second one silica, hydrophobic silica. The third one is combination between GO and silica. Yeah, the silica. All of the membrane shows that they have excellent salt rejection, and we can say that GO actually has a very good performance because of the flux is high, and we also combine between GO and silica, and we can say that like GO is the most excellent one. Silica, the second one is the silica with the hydrophobic structure, and the combination between GO and silica is good. We can say that it's not too good, yeah, to be too good if compared to the GO alone. Yeah, maybe this is from me. Yeah, thank you very much for the opportunity to share about our research. Kembali ke Bu Yayu, terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Pak Adi. So maybe I can give a review in your talk. So first you talk about the GO membrane for desalination, and then after that silica membrane. And then the last one is combination between silica and also graphene oxide to become a membrane. Okay, so ladies and gentlemen, now come to the discussion session. So for the audience who wants to ask to the speakers directly, please just use or raise your hands and then open cam. Or in another way, please just write down your question in the chat room. Anyone wants to ask? Okay, so maybe we can, I think we have some question in this chat room. First, okay, for Dr. Sumiyyah, okay. How to enhance the IO2 bound to cytosine layer? Okay, in your presentation, you talk about, you make the titanium dioxide and also chitosan layer by layer, so glass plate, and then after that chitosan, and then after that TiO2. And how to say, like, because it should be like interaction between titanium dioxide and also chitosan, and how to enhance the interaction between them or among them. So yeah, maybe in order to like avoid how to say, like probably how to make TiO2 embed into the chitosan very well. Okay, maybe like this, Dr. Sumiyyah.
Okay, thank you for the question. So, basically, the chitosan has a good film forming ability. It can attach to the glass plate very well. In fact, if you coated the chitosan on top of the glass and then after that you try to break the glass, it will not be broken because the bonding between the chitosan and the glass is very strong. And then in the TI2 formulation, we also add the adhesive, which is the epoxy natural rubber. So this has allowed the TI2 and the chitosan to interact very strong. Okay, and in terms of the efficiency between the chitosan and also the TI2, we also did a stability test using ultrasonication. We try to test the strength of the coating layer at different time or different condition, the strength of the ultrasonic, the power of the ultrasonic. So we choose the best composition of this titanium dioxide and also the chitosan. In terms of the photocatalytic efficiency, we have to get an optimum dosage of the chitosan and titanium dioxide onto the glass plate because the glass plate has a very limited area, so we have to make sure that we do not have too much of the chitosan or too much of the titanium layer. So it has to be like very right amount. And we do not want the chitosan to be too excess. If it's too excess, then the adsorption will be dominant. And we also do not want the titanium dioxide layer to be very thick because in this case, it'd be much more difficult for the pollutant to diffuse through the macropores. So we did optimization based on the dosage of the adsorbent and also dosage of the photocatalyst.
Okay, thank you. So the key point is the composition, yeah, the best composition.
Yes.
Okay, thank you, Dr. Sumiyyah. Okay, next question for Prof. Adi. Prof. Adi, when you change driving force from temperature per evaporation to pressure different, it will work very well when you change Prof. Adi?
Yes.
Okay.
Okay. So actually, just adjust the temperature from the 30 to 45 to 60. The pressure is constant because there is no change in the vacuum pump. I think that when we increase the temperature, how to say, the kinetics, what we call the molecular kinetics, the molecular kinetics increase by the increasing of temperature. So it increased the ability of the molecule to pass away, to pass the pore of the GO or the silica. So the idea is like this one. So the increasing of the temperature increase the molecule kinetics, the how to say, the speed of the molecule. So the energy of molecule increase and it can pass the pore more quickly compared to the lower temperature. This is the idea is like this one. So that the amount of the water that to be collected in cold trap is increased. Yes, that is the idea. Take this one.
Okay, thank you, Prof. Adi. Anyone who wants to ask to the speakers? Mr. Damar, maybe, or maybe Mrs. Tri. I think
Bahasa
Mrs.
Indonesia juga apa-apa kok. Pakai bahasa Indonesia
Yeah,
juga
you
apa-apa.
can use bahasa Indonesia as well. Okay, no one. Okay, maybe I have question, Dr. Sumiyyah. when you in the last talk you talk about nitrogen dope, right? Nitrogen dopes the titanium dioxide, and then you how to say you characterize the band gap. Yeah, and then because of the nitrogen doping, so the band gap of the photocatalyst will decrease, right? Uh, in terms of when you use titanium dioxide and also chitosan, I didn't see uh, I didn't see about the band gap characteristics. Is it important or not actually when we make like a how to say thin film TiO2 photocatalyst? Is it important or not to like how to say to identify the band gap? Or it's just how to say like because when we talk about photocatalysts we also talk about the band gap, right? Because the electron, I mean when the material is irradiated by the uh, energy from the how to say like solar cell solar or so or from the UV lamp, for example. So the electron will how to say like excite from the valence band to the conduction band. So the band gap is very important. But in this thin film, the titanium dioxide and chitosan, I don't know whether I miss or not about the band gap. Maybe you can explain, Dr. Sumiyyah. Thank you very much.
Okay, so the band gap energy is it's very important for photocatalytic study because we want to make sure that the aim is to improve the visible light active of the photocatalyst. So when we first did the titanium dioxide chitosan without any dye, and we use phenol as the pollutant, we observed that actually the chitosan itself also was oxidized, forming carbonyl groups. So with the presence of the carbonyl group, it has increased the visible light active of the photocatalyst. So I actually shared the band gap energy. When the chitosan was oxidized, the band gap energy reduced to 2.93 electron volt. And then when we add the dye into the chitosan, so you can also see the shift in the visible light region because the dye can absorb photon energy in the visible region. So it increases the band gap energy. That decreases the band gap energy. And then when we modify the chitosan with monomoronite, so it also has slightly decreased the band gap energy of the photocatalyst. Yeah, so even when you're doing thin film or in powder form, it is really important to know whether there are any changes in the band gap energy. So we do not want the band gap energy to be higher than the titanium dioxide alone. Thank you.
Okay, thank you, Dr. Sumiyyah. Okay, and then one more about the SEM images, I guess. You how to say like you present about the SEM images of the TiO2, chitosan, and also glass plate. Yeah, I guess so. And then with the black and white image, you show that this one is TiO2 and this one is chitosan. How you can determine that this is actually the titanium dioxide, where you don't like using like a mapping part of the image. Yeah,
Because
you get my point, right? Okay.
yes. Because the SEM images was conducted in cross section. It's not on the surface only. So it's a cross section because it's a layer by layer. So we did a cross section and we can clearly see the difference. So there's no need to do mapping because the chitosan is a very dense layer. So you can clearly see it's like a thin layer. Okay, while the chitosan titanium dioxide layer is more porous. So the two feature is very distinct. So you can differentiate between the layers. Yeah, and then the glass is just like solid glass like that. So you can see three significant difference between the layers. So that's why we didn't do any mapping for
Oh,
that
okay.
cross section.
Okay, okay, thank you. Because the difference is quite, how to say, clear, yeah.
Mhm.
So you do not need mapping.
But for the nitrogen dope carbon porous
Yeah.
titanium dioxide, yeah, we did do
Yeah.
mapping to
Mm,
determine whether there's presence of nitrogen, carbon, and titanium.
okay.
Yeah,
Yep. Okay,
because
thank
there is a composite.
Yeah, yeah. Okay, okay. Thank you, Dr. Sumiyyah. So, and the last question from me, Prof. Adi. You in your presentation, you said that when you use a low pH, so the how to say the interaction between GO and also silica is just like a hydrogen bond. But when you use a high pH, yeah, the interaction between silica and also GO become covalent bond. Maybe you can explain why it happens like that.
Very good question. Okay, let me share. Okay. Sorry. This this is the last slide, right? So actually, this is how to say the very nice question, but at the moment, we can say the pH dependent the protonation of this functional group at higher pH result in the both GO and silica negatively charged surface and makes ester bond. So actually, I can't answer the because this one is if we can say that this is this one is carboxylic structure, right? This is the carbolic
Yeah.
structure, this is a carboxylic structure, and this is the OH. Yeah, and if we in the low pH, it means that the
Concentration of
concentration
H.
of hydrogen is high. So we can see that this is the more carboxylic structure. But when the pH is
Ah, I see.
high,
Okay,
you can
okay.
see. So this
Yeah,
is
yeah.
one like the ester structure because the OH and the OH of the silica and this one the carboxylic structure. And when we change the pH, it's like reaction between the carboxylic and OH group, right? Like alcohol and carboxylic. You can see
Yeah.
the reaction between the alcohol and carboxylic is in high pH, not in the low pH.
Okay, okay, okay. I understand.
Is it?
So
Okay.
in high pH will be more
As
hydroxyl, a concentration of hydroxyl, right? So it can, how to say, like react with H from the
yeah,
carboxyl, yeah,
yeah.
carboxyls.
So
Okay, okay. Yeah. Is it validated with the data like FTIR or something else, Pak Adi?
okay. This is the should be in the FTIR.
Hmm.
How to say the concentration of
COC.
the OC. I forgot because I forgot the pH of the solution. Oh yeah, you can see this is the concentration of GO and the pH. And
Oh, but this.
it should be from this one, the structure of the between the COC and the OH.
Hmm.
Yeah, the what is this like the dip or the dip of the peak.
Hmm. The intensity,
Yeah,
yeah,
the
of the
intensity, the density of
transmittance.
the yeah.
Okay, okay. Yeah, thank you, Prof. Adi. Okay, okay. There is one question. Dapatkah kita memadukan antara membran dengan material fotokatalis sehingga dapat berfungsi sebagai pendegradasi satu warna sekaligus penyaring air? So yeah, can we how to select a mix membrane and also photocatalyst together in order to enhance the performance of the photocatalyst for dye degradation and also for the water filtration?
Yes, yes,
Yeah.
not for the desalination, not for desalination, but like for
Oh,
the
for desalination, okay.
not for desalination, but for like organics waste, like what my student did in the last semester with Akbar to 2020 student. He did how to say self-cleaning membrane, like membrane was put on a polymer layer, and but not GO. This he was using uh, graphitic carbon nitride and doped with, say I forgot. He doped the graphitic carbon nitride with copper, if I'm not mistaken. And after that, using for the what is the I forgot what is the dye is RBB. I think what is the RBB stand for? Actually, this is the dye.
Oh,
Yeah.
the
Whatever the
Remazole
dye.
Black B.
Yeah, Remazole Black B. Yeah,
Yeah.
RBB. Yeah, Remazole Black B. And this is like this is the layer of this membrane, not the membrane with the support is nylon, and put the graphite carbon nitrate doped with carbon oxide, sorry, copper oxide, and do the now filtration for the RBB, and the RBB was deposited on the first surface, and after the like 1 hour or more than 1 hour, the membrane was illuminated with UV, and like self cleanings of membrane, because membrane can, how to say, can degrade the falling of the falling because of the RBB, and like this one. So we can actually we can combine with the we can combine between the membrane and the photocatalyst membrane as also as photocatalyst. Yeah.
Okay. Okay. Dr. Sumiyyah, maybe you have any additional information regarding this question?
So my team and I, we never really did any membrane study before. But I think there are, based on the literature, there are studies related to photocatalyst that is coated onto the membrane. So it is possible to try to do the study, like Prof Adi mentioned. His student has already done on the self-cleaning. So that is also another good area to venture into.
Okay.
Thank you.
Okay, thank you, Dr. Sumiyyah. Anyone? Any questions?
So there's one direct message from
Oh, yeah.
she asked about the desalination performance for the seawater. Actually, no, because at the moment I just using the artificial seawater. Only use put the salt in the water, not the from seawater directly. So because she asked about the using of the seawater, but I and with my student have not.
Use
Yes, I have experience to using the direct seawater.
seawater. So salt water as a
Only
this as a
model.
seawater model, yeah. Okay. Okay, so I think time is over now. Yeah. Maybe if anyone wants to talk more about the topics, you can just send an email, or probably because the participants mostly are students, so maybe you can directly ask to Prof Adi if you want to ask about the membrane. So time is over, and then we finally come to the end of the joint webinar session. So we would like to say thank you very much for the keynote speakers, for the new insight and also knowledge sharing. And also thanks all of the participants or audiences here for your attention and also active participation. Hopefully this joint webinar series will give insight and also a benefit for us. So thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh. See
Waalaikumsalam.
you